There may be no final explosion, no last flash of light, and no single moment when the universe simply ends. Instead, galaxies may slip beyond one another's horizons. The last red dwarfs may fade. Black holes may evaporate through Hawking radiation, and the cosmos may drift toward heat death, a future where energy still exists. But almost no usable difference remains to make anything happen. If this kind of slow cosmic mystery feels worth spending time with, a subscription or share helps Calm Space Science continue creating thoughtful journeys through the deepest questions in science. And wherever this video has found you, leave a comment with your city or country and the time there, whether you're studying, relaxing, or listening before sleep. Thank you for choosing to spend part of your time here. From the final stars to the possibility of a universe with almost no events left at all, the story now moves toward the strangest question of all. What comes after an ending that may never truly arrive? The phrase "end of the universe" sounds as though it should describe a single event, a final boundary beyond which nothing remains. Modern cosmology gives a quieter and more complicated picture. The universe may never arrive at one universal instant of death. Instead, its future can be described by the long-term behavior of matter, radiation, gravity, expansion, and entropy, with different physical models leading toward very different kinds of endings. In one possibility, space continues expanding forever while galaxies separate, stars disappear, black holes evaporate, and usable energy becomes increasingly difficult to find. In another, expansion becomes so extreme that bound structures are eventually pulled apart. In still another, expansion reverses and the universe contracts. These possibilities are commonly associated with heat death, the Big Rip, and the Big Crunch, but the names can hide an important distinction. They are not merely three dramatic ways for everything to stop. They describe three different answers to a deeper question. What does it mean for a universe to reach a state from which its familiar history can no longer continue? For the universe as it is observed today, the most conservative long-term picture begins with expansion. Distant galaxies, on average, recede as space itself grows, and observations show that this expansion is accelerating rather than slowing under gravity alone. If that broad behavior continues indefinitely, there may be no final collapse, no universal flash, and no instant when existence simply switches off. There is instead a gradual loss of structure and usable contrast. Regions that are not gravitationally bound become more separated. The supply of gas available for forming new stars declines. Existing stars exhaust their nuclear fuel. Stellar remnants cool. Matter may itself face an uncertain future depending on whether protons are truly stable. Black holes can persist for timescales far beyond ordinary stellar evolution, yet even they are not necessarily permanent if Hawking radiation is part of the correct description of nature. The universe can therefore move through a sequence of increasingly sparse eras without ever encountering a single moment that deserves to be called the end. This is why Big Freeze and heat death are closely related but not perfectly identical ideas. Big Freeze emphasizes the physical cooling and dilution that accompany continued expansion. As wavelengths stretch and structures become isolated, the cosmic environment trends toward lower temperatures and lower densities. Heat death emphasizes the thermodynamic limit. Thermodynamics is the study of how energy is distributed and transformed, and one of its central ideas is entropy, a measure connected to the number of microscopic arrangements compatible with a macroscopic state. In ordinary language, entropy is sometimes described simply as disorder, but that shorthand can be misleading. What matters for the far future is that systems tend to evolve towards states in which energy differences become harder to exploit. A hot object beside a cold one can drive change because there is a temperature difference between them. A universe in which useful gradients have almost vanished may still contain energy, particles, and radiation. Yet it may no longer support the kinds of organized processes that depend on concentrated energy flowing into less energetic surroundings. In that sense, heat death does not mean that everything disappears. It means that the cosmos approaches a condition in which very little remains capable of doing anything interesting on a large scale. This distinction changes the emotional shape of the problem. A dramatic ending is easy to imagine because it resembles familiar events: an explosion, a collapse, a rupture. Heat death is harder because it is not an event in the same way. It is closer to an asymptotic condition, a state approached over ever longer spans as differences flatten out and accessible free energy declines. The universe can continue to exist while becoming increasingly uneventful. That possibility makes the phrase after the end unusually difficult. If there is no sharp ending, there may be no clearly defined afterward. There is only a later and later future in which change becomes rarer, slower, and less structured. The Big Rip offers almost the opposite kind of ending. It appears in certain models of dark energy in which the component driving cosmic acceleration becomes powerful enough that expansion grows without bound in a particularly aggressive way. Under those conditions, the increasing expansion could eventually overcome the forces holding structures together. Galaxy groups would separate, then galaxies, and in sufficiently extreme versions, even stars, planets, and smaller bound systems would no longer remain intact. The important scientific caution is that this is not the default prediction simply because the universe is accelerating. It depends on the detailed behavior of dark energy, especially on whether its effective pressure and density evolve in the required way. The Big Rip is therefore a legitimate theoretical possibility within certain cosmological models, but not an established forecast. The Big Crunch is different again. It imagines a universe in which expansion eventually halts and reverses, allowing gravity to draw the cosmos back toward a denser state. Earlier discussions of cosmic destiny often focused heavily on this possibility, because the average density of matter seemed closely tied to whether expansion could continue forever. The modern picture is more complicated because dark energy changes the dynamics. With the observed accelerated expansion, a simple future collapse is not the favoured outcome of the standard cosmological model. Yet the Big Crunch remains useful because it shows how strongly cosmic fate depends on the properties of the components filling space. If the behaviour of dark energy were different from the simplest assumption, or if the effective rules governing expansion changed over immense timescales, the distant future could look very different from a permanent freeze. None of these scenarios should be treated as a complete description of everything that could happen. They are ways of extending known physical laws and cosmological measurements into regimes far beyond direct observation. That extrapolation is unavoidable. No experiment can wait through the death of the final star or watch the universe over timescales so vast that ordinary intuition stops being useful. Cosmology therefore combines present observations with physical theory, asking what follows if the laws measured now continue to operate. The farther those calculations reach, the more carefully certainty has to be separated from assumption. Even a well-motivated scenario can depend on quantities that remain poorly understood. Dark energy is the clearest example. Its existence is inferred from the observed expansion history of the universe, but its fundamental nature is still unknown. If it is a constant property of space, the long-term picture points in one direction. If it evolves, weakens, strengthens, or reflects deeper physics not yet understood, the destination can change. That uncertainty means the end of the universe is not a single prediction waiting on a distant calendar. It is a family of futures constrained by what is known and opened by what is not. There is another sense in which the universe can end without vanishing. Much of what makes the present cosmos recognizable depends on persistent differences. Stars are hot against colder space. Matter gathers into galaxies rather than remaining uniformly spread. Chemical systems exploit gradients. Life, wherever it may exist, relies on flows of usable energy. Even observation depends on events that leave records and signals. A future in which those differences have nearly disappeared would not be empty, but it would be physically impoverished compared with the present. The universe might contain particles too widely separated to interact often, photons stretched to extremely low energies, and remnants so isolated that meaningful encounters become fantastically rare. From this perspective, cosmic death is less about the destruction of substance than the erosion of possibility. The question becomes not when everything ceases to exist, but when the conditions required for complex change fade beyond practical recovery. That is why the most likely ending discussed in standard cosmology is both less violent and more profound than the word ending suggests. It may unfold through the gradual disappearance of opportunities for structure, reaction, radiation, and renewal. There may be no final observer to mark a last second, no universal clock announcing completion, and no boundary after which existence becomes non-existence. There may only be a universe moving deeper into a state where almost nothing new can happen. Before that distant condition can be understood, however, one present-day uncertainty has to be placed at the center of the story, because the future depends on what is already driving expansion now. The question of how the universe ends begins with the still unresolved nature of dark energy. Dark energy does not announce itself through light, particles, or a visible structure in space. Its presence enters cosmology through the behavior of expansion. When astronomers compare the distances of remote galaxies with the way their light has been stretched, the universe does not look as though gravity is steadily slowing its growth. Instead, the expansion has been accelerating during the more recent part of cosmic history, which means that something in the large-scale energy budget of the universe behaves in a way ordinary matter cannot explain. Dark energy is the name given to that missing component. The name sounds more definite than the knowledge behind it. It identifies an effect and a place in the equations, but it does not yet identify a known substance. In the standard cosmological model, the simplest description treats dark energy as a cosmological constant, an energy associated with empty space whose density remains unchanged as the universe expands. Matter thins as space grows because the same amount of matter becomes spread through a larger volume. A cosmological constant does not dilute in the same way. As a result, once matter becomes sufficiently sparse, this nearly uniform component begins to dominate the large-scale dynamics. That transition is already part of the observed history of the universe, and it places dark energy at the center of every serious attempt to describe the distant future. If it truly remains constant forever, then continued accelerated expansion becomes the natural expectation. Structures already held together by gravity can survive locally, but distant, unbound regions separate ever more rapidly. The future then points toward isolation, fading starlight, black hole evaporation, and eventually the cold thermodynamic condition associated with heat death. Yet this entire chain rests on a remarkable assumption that whatever dark energy is, its behavior on timescales far beyond the present will remain the same as the behavior inferred today. Cosmology has reasons to use that assumption, because the cosmological constant provides an economical fit to a wide range of observations, but economy is not identity. A successful parameter in a model is not automatically a complete explanation of nature. This is where measurements of cosmic history become unusually important. Dark energy cannot be placed in a laboratory and watched across billions of years. Instead, astronomers use the universe itself as a record. Light arriving from different distances left its sources at different times, so large surveys can reconstruct how expansion changed as the cosmos aged. One of the central tools in this effort is the Dark Energy Spectroscopic Instrument, or DESI, which measures the spectra of enormous numbers of galaxies and quasars and builds a three-dimensional map of their distribution. Embedded in that distribution is a statistical scale known as the Baryon acoustic oscillation feature, a faint imprint left by sound waves that moved through the hot early universe before atoms formed. Because the physical scale of this imprint can be predicted and calibrated, its apparent size at different epochs acts as a kind of cosmic ruler. The way that ruler appears across distance and time constrains how rapidly space has expanded. DESI is therefore not looking for dark energy as an object. It is measuring the geometry and growth of the universe with enough precision to ask whether the simplest dark energy history remains adequate. The importance of that distinction is easy to miss. A small change in the inferred behavior of dark energy does not merely adjust one number in a cosmological table. It changes the shape of the future. Results based on the first several years of DESI observations strengthened an earlier hint that dark energy may not be perfectly constant when the DESI measurements are combined with other major cosmological data, including observations of the cosmic microwave background and exploding stars used as distance indicators. The statistical preference depends on which external data sets are combined, and it has not reached the level required to declare a discovery. The safest statement is therefore not that dark energy has been shown to evolve, but that the constant dark energy picture is under a more interesting test than it was before. That caution matters because cosmology has seen tensions rise and weaken as measurements improve, calibrations change, and hidden systematic effects are better understood. A pattern can be scientifically important long before it becomes established. DESI has now completed the observing program originally planned for its main survey and has mapped tens of millions of galaxies and quasars. While observations continue beyond that initial plan, more data can tighten the range of possibilities, but the decisive issue is not simply quantity. Different probes have different sensitivities and different sources of uncertainty, so confidence grows most strongly when independent methods converge on the same physical picture. If future observations continue to favor evolving dark energy, the consequences would extend far beyond the fate of distant galaxies. A changing dark energy component could indicate that the phenomenon is produced by a dynamical field rather than by a true constant of empty space, or that the standard description of gravity and cosmic expansion is incomplete. Many theoretical models can imitate some form of evolution, and that abundance is itself a warning. Detecting departure from a cosmological constant would be only the beginning of the explanation, not the end. The direction of change would matter as much as the fact of change. If dark energy weakens sufficiently over cosmic time, accelerated expansion might eventually become less dominant. That would not automatically produce a future collapse, because matter density, spatial geometry, and the detailed evolution of the dark component would still have to be considered together. If dark energy instead behaved in a way that made its repulsive influence grow more extreme, some models could move toward the conditions associated with a big rip. Other forms of evolution might lead to futures that fit neither familiar label. The far future is therefore unusually sensitive to physics that currently appears only as a subtle difference in measurements of the past. This sensitivity is why statements about the end of the universe carry different levels of confidence. The observation that cosmic expansion is accelerating is strongly established. The interpretation of that acceleration through a cosmological constant is highly successful, but not known to be fundamental. The possibility that dark energy evolves is actively investigated and supported by suggestive combinations of current data, but it remains unsettled. Predictions of heat death, the Big Rip, or eventual recollapse then sit one step farther out, because they require extending one of those possible behaviors across intervals of time that no observation can directly test. There is no contradiction in treating heat death as the leading long-term scenario while also admitting that the foundation beneath it is incomplete. Science often works by ranking futures rather than pretending that uncertainty has disappeared. At present, continued accelerated expansion under a dark energy component close to a cosmological constant provides the cleanest path toward a cold and increasingly dilute cosmos. But the measurements are now precise enough that small departures from that simple picture can be examined rather than ignored. That changes the character of the question. Cosmic destiny is no longer determined only by how much matter exists, or whether gravity can pull it back together. It depends on the properties of something that fills the universe smoothly, dominates its present energy budget, and has never been directly identified. The most distant future is therefore connected to one of the most immediate problems in observational cosmology. Before considering dying stars or evaporating black holes, the expansion itself establishes the stage on which all of those events occur. If acceleration persists indefinitely, the first major transformation will not be the destruction of galaxies but their separation. Beyond the gravitationally bound structures of the local cosmos, more and more of the universe will recede toward horizons that no later signal can cross. The end begins not with disappearance, but with distance. The local group will not be carried apart by cosmic expansion. Its galaxies are bound strongly enough by gravity that the growth of space on larger scales does not simply pull them away from one another, and over very long periods their internal motions will continue to reshape the region. Beyond that gravitational island, however, the situation is different. Galaxies that are not bound into the same local structure participate in the large-scale expansion of the universe. And as accelerated expansion continues, the distances between such regions increase more and more rapidly. The important change is not that those galaxies suddenly begin moving through space at impossible speeds. The geometry between distant structures grows. Light attempting to cross that expanding separation must travel through a universe whose scale is changing while the journey is underway. At the present epoch, astronomers can still receive light from galaxies at enormous distances because the photons began their journeys when those galaxies were closer, and because the expansion history of the universe has allowed that light to reach this region. But future visibility is governed by a different question: whether light emitted at some later time will ever be able to overcome the increasing expansion between its source and an observer. Under a long-lasting form of accelerated expansion similar to the one described by a cosmological constant, there is a cosmic event horizon. It marks a limit not of what can be seen now, but of what can ever communicate with a given location in the far future. A galaxy beyond that effective causal boundary may still exist, form stars, merge with companions, and evolve in ordinary ways inside its own region. Yet light emitted from sufficiently late stages of its history will never arrive here. The separation does not have to destroy either side. It only has to become large enough and grow quickly enough that future signals can no longer bridge it. This is one of the quietest ways the universe can become smaller without space itself shrinking. The physical universe may continue expanding, but the portion that remains causally accessible from one location can become increasingly limited. For any civilization surviving in the distant future within a gravitationally bound galactic remnant, this would alter the appearance of the cosmos profoundly. Nearby bound stars and stellar remnants would remain. but the broad population of external galaxies would fade from view. Their light would be stretched to longer and longer wavelengths as space expands during its passage. This cosmological redshift would not merely change the color of the signal, it would reduce the energy carried by each photon and spread successive photons farther apart in arrival time, weakening the observable flux. A distant galaxy would therefore not disappear like a lamp being switched off. It would dim, redden, and become harder to detect until its continuing history was effectively hidden beyond the horizon. The distinction between distance and visibility matters because the universe already contains regions whose present recession rate, defined through the expansion of space, exceeds the speed of light without violating relativity. Relativity forbids objects from locally outracing light through nearby space, but it does not require the distance between very remote regions in an expanding geometry to increase more slowly than light. Some galaxies whose present separation grows at such rates are still visible because the photons now arriving were emitted long ago under different expansion conditions. What determines their ultimate accessibility is the full history of expansion, not a simple snapshot of recession speed. This makes the future horizon a property of cosmic dynamics rather than a wall located at a fixed distance. As time passes in an accelerating universe, more unbound regions become unreachable in the practical causal sense that no new signal sent from them can ever arrive. The same separation works in both directions. Future signals originating here would also fail to reach sufficiently distant regions. Large-scale cosmic history therefore fragments into isolated domains, each containing matter that remains gravitationally connected within itself while losing contact with domains beyond its horizon. The universe as a whole does not need to break apart for its history to become locally sealed. This has an unusual consequence for knowledge. Present-day cosmology is possible partly because the sky preserves information from many epochs and many scales. Distant galaxies reveal earlier stages of galactic evolution. The cosmic microwave background carries information from a time when the universe was young, hot, and filled with an ionized plasma before neutral atoms could persist. The distribution of galaxies preserves traces of the growth of structure. Expansion itself can be reconstructed by comparing objects observed across different distances and therefore different periods of cosmic history. Much of that evidence depends on access to a large external universe. In the far future, an observer inside the surviving bound region would inherit a much poorer sky. External galaxies would have faded away. Their light would be shifted beyond increasingly inaccessible wavelengths. Even relic radiation from the early universe would be stretched and diluted towards states that are extraordinarily difficult to measure. The evidence that once made cosmic expansion obvious could become almost impossible to recover from direct observation. A future astronomer might live in a universe that is still expanding rapidly on scales beyond the local gravitational system, and yet see almost none of the structures that reveal that expansion. The local sky could give the impression of a solitary galaxy surrounded by darkness, even though that darkness contains remote regions with their own stars and remnants beyond causal reach. The fading of galaxies is therefore not only a transformation of scenery, it is an erosion of observable cosmic context. The universe retains its history, but access to that history becomes uneven. Information carried by light can be lost to horizons even when the objects producing it continue to exist. This is a useful reminder that the observable universe is not identical to the entire universe. The observable region is defined by which signals have had time, under the actual expansion history, to reach a particular observer. Its boundaries depend on both time and cosmology. A future observer does not simply receive a larger and larger archive forever. Accelerated expansion can remove classes of future information faster than the passage of time makes new regions accessible. The result is a strange reversal of intuition. In a static space, waiting longer would usually allow light from farther away to arrive. In an accelerating universe, waiting longer can instead mean that some distant sources are becoming permanently less connected. Their old light may still arrive for a time, but later chapters of their existence are excluded. The sky becomes an archive with pages that grow fainter, while the unwritten pages can no longer be delivered. Gravitational binding creates the exceptions. A galaxy group, or sufficiently dense local structure can resist the background expansion, because the matter inside it is not merely following the general Hubble flow. Local gravity controls its motions. Within the local group, the Milky Way and Andromeda are already moving toward a future interaction rather than being driven apart by expansion. Their eventual merged descendant, together with other material that remains bound, would form part of the long-lived island from which the external universe gradually disappears. This does not mean gravity defeats cosmic acceleration everywhere. It means the universe separates into scales where different effects dominate. Inside bound systems, gravity shapes the future. Between sufficiently distant unbound systems, accelerated expansion increasingly controls the separation. That division grows more consequential with time. The galaxies beyond the local island are not erased, but they become irrelevant to its later physical history because they can neither send newly emitted signals across the horizon nor receive signals sent too late from here. Causal contact narrows toward the structures already held together, long before the final stars burn out. The cosmos therefore undergoes a kind of geographical ending. Not all matter disappears, and not all light ceases, but the connected universe contracts in an informational sense. Each surviving bound region becomes a more isolated repository of matter, memory, and local evolution. The grand web of galaxies that fills the present observable universe becomes less like a shared landscape and more like a set of separated islands whose later histories can never meet. That isolation is the first great simplification of the far future. Once the external universe has faded beyond reach, the remaining story is carried by what each island still contains. The next limit is no longer distance between galaxies, but fuel inside them, because even a perfectly bound cosmic refuge cannot keep producing new stars forever. Star formation does not end because the universe suddenly loses the ability to make stars. It fades because the raw material becomes harder to gather, harder to cool, and increasingly locked inside objects that no longer return much of it to space. In the present universe, stars are born inside cold molecular clouds, dense regions where gravity can overcome pressure and turbulence strongly enough for gas to collapse. Much of that gas is hydrogen left over from the early universe, mixed with heavier elements produced by earlier generations of stars. The process is already part of a long cycle. Gas collapses into stars. Stars fuse light elements into heavier ones. Stellar winds and explosions return some of that material to surrounding space, and later clouds use the recycled material again. The cycle is not perfectly efficient. Some matter ends up trapped in long-lived stars, white dwarfs, neutron stars, black holes, planets, or gas that becomes too hot or too diffuse to collapse easily. Over very long timescales, the available reservoirs of cold star-forming gas decline. Galaxies can acquire fresh gas from their surroundings, and collisions between galaxies can compress existing material and trigger new episodes of star formation. But those sources are not unlimited either. As the universe expands and bound regions become more isolated, the large cosmic circulation of matter weakens. Inside each surviving gravitational island, star formation becomes increasingly dependent on whatever usable gas remains locally available. The decline begins long before the final star appears. Observations of galaxies at different cosmic ages already show that the universe formed stars much more rapidly in the past than it does now. The period of greatest stellar production occurred billions of years ago, when galaxies contained larger supplies of cold gas and interactions were more frequent. Since then, the overall rate of new star formation has fallen. That decline is not evidence that stellar birth is close to stopping on ordinary human or geological timescales. It is the early part of a process that unfolds over spans vastly longer than the current age of civilization or of the Earth itself. The important point is directional. The stellar universe has passed its most productive era. What remains is a slow withdrawal from abundance. Massive stars disappear first because brightness is expensive. A very massive star can contain far more fuel than a small star, yet it consumes that fuel at an enormously faster rate, because the pressure and temperature in its core drive fusion with much greater intensity. Such stars may shine for only a few million years before exhausting the fuel needed to support their cores. Their deaths can be violent, producing supernova, neutron stars, or black holes, and returning part of their outer material to space. Stars more like the Sun live far longer. But even they have finite reserves. Eventually, hydrogen fusion in the core can no longer continue in the same stable form. The star changes structure, expands, loses outer layers, and leaves behind a dense remnant. Across the far future, each generation removes some fraction of the remaining gas from easy circulation. The brightest stars therefore vanish repeatedly and quickly, compared with the lifetime of the smallest stars, while the general population gradually shifts toward dimmer and longer-lived objects. Red dwarfs become central to this late stellar era because they use their fuel with extraordinary patience. They are small, cool stars with masses well below that of the Sun, and their interiors allow hydrogen to be consumed much more completely than in larger stars. In a star like the Sun, only part of the available hydrogen spends enough time in the hot central region to participate directly in core fusion before later stages of evolution begin. Many red dwarfs are much more thoroughly mixed internally, allowing fresh hydrogen to circulate into fusion regions while helium produced by fusion is carried elsewhere. Their lower temperatures also mean their nuclear reactions proceed slowly. The combination gives them lifetimes that can reach trillions of years, far beyond the present age of the universe. No red dwarf has yet had time to complete its full natural life cycle. The universe is simply too young. Every example now observed belongs to an early phase of a lifespan that may extend through epochs in which nearly every familiar bright star has already disappeared. This makes the red dwarf a useful symbol of the transition between the luminous universe and the remnant universe. It is not spectacular in the usual sense. Its importance comes from endurance. Long after massive blue stars are gone, long after stars resembling the Sun have become remnants, red dwarfs can continue releasing energy at low rates into increasingly dark surroundings. Their light may be modest, but in a future where luminous objects have become rare, modest light becomes the dominant kind. The decline of star formation changes galaxies as well. Spiral arms are visually prominent today partly because they contain regions of active stellar birth, including short-lived massive stars that shine intensely and illuminate nearby gas. As new star formation weakens, galaxies lose much of that youthful contrast. Their remaining stellar populations age, massive stars vanish, then intermediate mass stars follow, leaving long-lived low-mass stars as a growing fraction of what still shines. The galaxies themselves may already have changed shape through mergers and gravitational encounters before this stage becomes dominant. In isolated bound regions, repeated interactions can eventually produce large, smooth stellar systems containing old stars, remnants, central black holes, and whatever gas has not been expelled, heated, consumed, or locked away. The familiar distinction between actively forming spiral galaxies and older elliptical systems becomes less meaningful once the supply of new stars has nearly ended everywhere. There is no single moment when the universe crosses from the age of stars into the age after stars. Different environments exhaust their gas at different rates. Small pockets of cold material may continue forming new stars long after most galaxies have become inactive. Stellar collisions or unusual gravitational interactions can occasionally create objects that resemble renewed stars even in very old systems. Some brown dwarfs, which are too small to sustain ordinary hydrogen fusion, may collide or merge under rare circumstances and produce a star where none would otherwise have formed. These events do not reverse the overall trend. They are isolated exceptions inside a cosmos whose main reservoirs of star-forming material have already been depleted. The distinction between possible and common becomes crucial. Star formation may remain physically possible in scattered locations long after it has ceased to be an important cosmic process. Eventually, even those exceptions become rarer. Gas that remains unbound can be driven away. Gas captured by stellar remnants may not return. Material locked into low-mass stars stays there for extraordinarily long intervals before those stars complete their evolution. In some systems, repeated gravitational encounters eject stars and compact objects into intergalactic space, removing them from dense environments where interactions are more likely. Every mechanism does not point toward the same immediate outcome, but together they reduce the ability of matter to reorganize itself into fresh generations of ordinary stars. The universe does not run out of hydrogen in the simple sense that every hydrogen atom is fused. Much hydrogen may remain in forms or locations where it is no longer accessible to efficient star formation. A resource can survive while the process that once used it becomes effectively extinct. This is one of the deeper patterns of the far future. Cosmic evolution is controlled not only by what exists, but by whether matter and energy remain arranged in ways that allow change to continue. During the stellar era, gravity repeatedly concentrates gas until nuclear fusion becomes possible. That concentration produces enormous differences in temperature, density, and radiation, and those differences drive rich physical and chemical activity around stars. When star formation fades, one of the universe's most important engines for creating such gradients begins shutting down. Existing stars still provide energy, but there are fewer replacements. The luminous inventory becomes a declining inheritance. Red dwarfs stretch that inheritance almost beyond imagination, but their longevity does not make them permanent. They too eventually exhaust the hydrogen available for fusion. Their detailed late evolution differs from that of larger stars, and the smallest may avoid the dramatic giant phases associated with stars like the Sun. Over enough time, however, stable nuclear burning ends. What remains is no longer a star powered by ongoing fusion. The last red dwarfs become compact remnants and slowly surrender their residual heat to space. By then, the era in which starlight dominates the visible cosmos has closed not through a catastrophe, but through attrition. The final star is unlikely to know that it is final. There is no physical signal announcing that no natural stellar birth will follow, somewhere inside an ancient bound system. A low-mass star simply continues consuming its remaining fuel, while the rest of the universe has already become overwhelmingly dark. Its output decreases, its internal composition changes, and eventually the process that defined stars for so much of cosmic history can no longer continue. The significance of that moment exists only in retrospect. After it, the universe still contains enormous amounts of matter, but almost all of the familiar luminous machinery has been replaced by remnants, white dwarfs, neutron stars, black holes, planets, brown dwarfs, and scattered debris remain, carrying the memory of the stellar age in structures that no longer shine by sustained fusion. The universe has not ended, but one of its longest and most productive chapters has. What follows is not emptiness. It is the beginning of a darker epoch in which dead stars outnumber living ones completely. And even the warmth stored inside those remnants begins its slow escape. When the last ordinary stars have finished burning, the universe does not become empty. It becomes a place dominated by leftovers, white dwarfs, neutron stars, black holes, brown dwarfs, planets, and scattered smaller bodies persist long after sustained stellar fusion has disappeared from most regions. These objects are not equally common, equally massive, or equally long-lived, but together they define a new cosmic age in which the bright processes that once organized galaxies have largely ceased. A white dwarf begins as the exposed core of a star that was never massive enough to collapse into a neutron star or black hole. After such a star exhausts the fuel needed for its final stages of fusion, it sheds much of its outer material and leaves behind a compact object roughly comparable in mass to a star but compressed into a volume closer to that of a planet. No continuing fusion supports it. Instead, its structure is held up by quantum mechanical pressure from densely packed electrons. At first, a white dwarf can remain extremely hot because it carries the thermal energy stored during the life and death of its parent star. It shines not by creating new energy in its center, but by releasing energy it already possesses. That distinction becomes important in the far future. A white dwarf is a cooling object, and given enough time it must become dimmer. Its temperature falls as radiation leaks into space, and its luminosity declines with it. The process is extraordinarily slow because the object is small, dense, and capable of retaining heat for immense intervals. Even so, there is no known source within an isolated white dwarf that can preserve its warmth forever. If the broad laws used to describe stellar remnants remain valid over fantastically long durations, a white dwarf should eventually cool until it emits almost no detectable visible light. The hypothetical object at that limit is called a black dwarf. The name can be misleading if treated as though it describes a separate class already waiting to be discovered. No black dwarf is expected to exist today. The universe has not existed for nearly enough time. Even the oldest white dwarfs have had only a fraction of the interval required to approach such an extreme state of cooling. A black dwarf is therefore not an observed object, but a prediction about what a white dwarf might become in a remote future. Its existence depends on extrapolating familiar physics far beyond any timescale available for direct confirmation. That makes it both scientifically useful and conceptually strange. It represents a category of object defined by the future rather than the present. Neutron stars follow a different history. They form when the core of a sufficiently massive star collapses and matter is compressed until atoms can no longer retain their ordinary structure. Protons and electrons are driven into a much denser state dominated by neutrons and other particles under conditions that cannot be reproduced on comparable scales in laboratories. A neutron star contains stellar mass within a sphere only a small fraction of the diameter of an ordinary star. Its density is so high that gravity at its surface is extreme, and young neutron stars can rotate rapidly, carry intense magnetic fields, and emit radiation in narrow beams. Pulsars are neutron stars whose rotating emission can sweep across space with remarkable regularity. None of that activity is permanent. Rotation gradually slows. Magnetic energy changes. Thermal energy escapes. A neutron star that begins as a brilliant radio or X-ray source can eventually become quiet and difficult to detect. leaving behind a compact mass whose internal structure still reflects physics at enormous density but whose outward signs have nearly vanished. In the remnant era, such an object may survive not because it remains active, but because there is little left capable of changing it quickly. Black holes occupy the far end of this progression in compactness. Some are produced by the collapse of massive stars, while supermassive black holes grow in galactic centers through a more complicated history of accretion and mergers. During the active life of galaxies, black holes can be surrounded by brilliant disks of hot matter and can power some of the most luminous phenomena in the cosmos. The black hole itself is not the source of that light. The radiation comes from matter heated as it falls inward before crossing the event horizon. When the surrounding supply of gas declines and stars become sparse, those luminous environments fade. The black holes remain, dark and difficult to notice except through their gravitational influence or through rare interactions with matter that passes nearby. This produces a reversal in what dominates the universe. During the stellar era, the most obvious structures are the ones that emit energy continuously. During the remnant era, longevity belongs increasingly to objects that do very little. They persist because there are fewer processes left to alter them. A cooling white dwarf can spend spans beyond ordinary comprehension, releasing ever smaller amounts of heat. A neutron star can remain as an almost invisible compact body after its pulse has faded. A black hole can survive while the galaxy that once fed it becomes sparse and dynamically old. The universe becomes less defined by creation and more by endurance. Yet even the word remnant can suggest more stability than the future actually guarantees. These objects continue to move through gravitational systems. Stars and remnants can pass near one another, exchange energy, form binaries, merge, or be thrown onto new trajectories. In dense environments, repeated encounters can slowly rearrange entire populations. A compact object may capture a companion. Two remnants may spiral together if energy is removed from their orbit. A wandering body may be ejected into intergalactic darkness. These events become increasingly uncommon as systems disperse. But immense time allows rare processes to matter. The architecture left by the stellar age is therefore not frozen in place. It keeps evolving, only at a pace so slow that the word evolution begins to describe isolated events, separated by enormous quiet intervals. White dwarfs may undergo additional changes as they cool. Their interiors are expected to crystallize as temperature falls, turning matter that once behaved more like a dense fluid into an ordered, solid structure. This is not a sudden freezing of the entire star, but a gradual phase change, beginning under conditions set by pressure, composition, and temperature. In the distant future, a fully cooled remnant could become an object whose matter is locked into a state unlike anything seen on planetary scales. The idea of a black dwarf therefore carries more than darkness. It represents matter that has passed through nuclear burning, stellar expansion, mass loss, compression, and an almost inconceivably long cooling history before reaching a state with very little remaining thermal light. Its silence is the final result of a star having already spent nearly every accessible source of brightness. The fate of such remnants then begins to overlap with more uncertain physics. If protons eventually decay, even a cold stellar remnant may not remain intact forever. Its constituent matter could slowly disappear into lighter particles and radiation over timescales determined by a process that has never been observed. If protons are completely stable, the object could persist for far longer, and other mechanisms would become more important in deciding its eventual fate. Similar uncertainties apply to neutron stars, planets, and other surviving structures. The remnant era is therefore not a single settled sequence with known dates for every transition. It is a framework built from known stellar physics joined to unanswered questions about the deepest stability of matter. What is clear is the direction of the change. The universe moves away from ordinary stars and toward compact, cooling, inactive objects. Light becomes rarer. Interactions become less frequent. Large systems continue to thin as members are lost through gravitational encounters. The remaining energy is increasingly trapped in forms that are difficult to access or spread across distances that make exchange unlikely. Even before matter itself is considered, the cosmos has already become almost unrecognizable compared with the present. A sky filled with active stars has given way to one dominated by objects that either barely glow or do not glow at all. Black dwarfs, if they eventually form, would be among the clearer symbols of that transformation, because none can exist until the universe has spent an enormous amount of time cooling. Their absence today is not evidence against them. It is evidence of how early the present universe still is. The remnant age lies so far ahead that even the oldest white dwarfs now known are only beginning a journey whose endpoint cannot yet be observed. By the time that endpoint is reached, planets and stellar systems around them will also have had vast intervals to change. Orbits can be disturbed, companions can be lost, collisions can occur, and isolated worlds can drift into darkness far from any remaining source of warmth. The death of the last star, therefore, does not leave behind a static museum of stellar corpses. It leaves a gravitational landscape that continues to rearrange itself long after light has ceased to define it. A planet does not need a living star in order to keep moving. Long after fusion has ended, worlds can continue circling white dwarfs, neutron stars, black holes, brown dwarfs, or the fading centers of systems that once looked much like the solar system. Their orbits may remain orderly for spans that dwarf the entire present age of the universe, but stability over ordinary astronomical time is not the same as stability forever. Gravity never stops acting. Every surviving body continues to tug on every other one, and across sufficiently long intervals, even extremely small exchanges of energy and angular momentum can accumulate. The result is a future in which planetary systems are not simply frozen in place after their stars die. They keep evolving, often so slowly that nothing appears to happen for immense stretches, until a rare encounter changes the architecture at once. The first disruptions can begin during stellar death itself, when a star loses mass. The gravitational field binding its planets weakens, orbits expand, and bodies that were comfortably separated can find themselves in new dynamical relationships. A planet close to an expanding giant star may be engulfed or destroyed, while planets farther away can survive but shift onto wider paths. If the central star becomes a white dwarf, the system that remains may bear little resemblance to its earlier arrangement. Asteroids, comets, moons, and planets can be scattered inward or outward, sometimes sending material toward the compact remnant. Observations of polluted white dwarfs in the present universe already show that rocky debris can fall onto stellar remnants, indicating that planetary systems continue to rearrange themselves after ordinary stellar evolution has ended. In the far future, the same basic gravitational processes have much longer to work. Multibody systems are especially important because gravity couples every orbit to the others. A planet can repeatedly exchange tiny amounts of orbital energy with neighboring planets. Most exchanges do not produce a dramatic outcome, but over enough time the system can wander through a vast range of configurations. Resonances can amplify certain interactions. Close approaches can suddenly transfer large amounts of energy. A body can be thrown toward the central remnant, collide with another object, or receive enough energy to escape the system entirely. The exact future of any particular planetary system is difficult to calculate over extreme timescales, because chaotic dynamics magnify tiny uncertainties in initial conditions. Chaos does not mean that anything can happen without rules. The equations remain deterministic, but the detailed outcome becomes increasingly sensitive to differences too small to measure perfectly. That makes the remote fate of individual worlds uncertain, even when the broad classes of possible outcomes are well understood. Ejection is one of the most important of those outcomes. A planet that gains enough orbital energy during a gravitational encounter can leave its parent system and become a free-floating world. Such planets already exist in the present galaxy, produced either during the formation of planetary systems or through later dynamical scattering. In an ancient remnant-dominated universe, the same mechanism can continue populating interstellar and eventually intergalactic space with isolated bodies. A world that once received regular warmth from a star may end up moving through darkness, with no permanent luminous companion. Its atmosphere, if it retains one, would cool. Surface liquids would freeze unless internal heat or unusual atmospheric conditions allowed some fraction to persist. Radioactive decay, tidal deformation, or residual heat from formation might continue supplying energy from within for a time, but these sources also decline or depend on specific circumstances. The future of such a planet becomes a problem of internal energy rather than sunlight. Some worlds may preserve subsurface layers or geologically active regions for surprisingly long intervals. Yet the overall trend is toward colder and more weakly powered environments. Collisions provide another route away from orderly planetary systems. In a crowded or destabilized system, two planets can cross paths and eventually strike one another. Smaller bodies may be shattered, accreted, or scattered. A surviving planet can also be driven inward toward a white dwarf, neutron star, or black hole. Close to a compact object, tidal forces can become destructive, pulling a planet apart before direct impact occurs. Around white dwarfs, disrupted asteroids and planetary fragments can form debris disks and gradually fall inward. Around neutron stars and black holes, the gravitational environment can be even more extreme. These encounters are rare compared with the quiet persistence of stable orbits. But vast time changes the meaning of rare. A process with an extremely low probability per unit time can still become important when the available interval is almost unimaginably long. Planetary systems can also be altered from the outside. Stars and remnants move through galaxies, and in dense regions they sometimes pass near one another. A close stellar encounter can perturb distant planets and comet-like reservoirs, changing orbits that had remained stable for billions or trillions of years. In star clusters, repeated encounters can strip planets from their hosts more efficiently. Even in less crowded environments, the cumulative effect of passing objects can slowly reshape the outer parts of a system. As galaxies themselves age dynamically, gravitational interactions between stars and remnants can cause some members to lose energy and sink toward denser regions while others gain energy and are ejected. This slow redistribution can eventually thin bound systems and send stars, remnants, and planets into wider or completely unbound trajectories. The surviving universe therefore becomes not only darker, but more dispersed. Some objects remain gathered around compact remnants, while others are thrown into almost empty space where the chance of another close encounter becomes extremely small. For a planet, isolation can become nearly permanent. Once a world is far from dense stellar environments and no longer bound to a star. There may be little capable of changing its motion. It simply follows a trajectory through expanding space, carrying whatever structure it still possesses: a frozen crust, a metallic core, an atmosphere collapsed onto the surface, or a collection of moons can persist even when no external light reveals them. The planet remains a physical object with a history, but most of that history is no longer expressed through active surface change. If internal heat fades and external encounters become negligible, its future can approach a state of extraordinary stillness. Yet even such stillness is conditional. The ultimate survival of planets depends on the stability of the matter from which they are made. If protons are stable forever, then a cold planet may remain as a bound object for durations far beyond stellar evolution, subject to only exceedingly slow gravitational or quantum processes. If protons decay, then the apparent permanence of rock, metal, ice, and degenerate stellar matter becomes temporary on a deeper timescale. The entire meaning of a dead planetary system changes. Instead of waiting indefinitely in darkness, its atoms would themselves participate in a gradual transformation into lighter particles and radiation. That question cannot be settled by planetary dynamics, because it belongs to particle physics, and present experiments have not observed proton decay. Until that uncertainty is resolved, the far future of matter divides into fundamentally different branches. The fate of planets therefore sits at a boundary between well-tested gravitational evolution and more speculative physics. Gravity can explain how systems scatter, merge, eject, and disperse. Stellar evolution can explain how the central source of light changes and dies. Thermodynamics can describe cooling, but none of these alone determines whether the material remains intact forever. What can be said with confidence is that the familiar architecture of a planetary system is not protected simply because the star has already died. Orbits are temporary arrangements maintained by gravity, and over extreme time their slow interactions can erase the ordered patterns that once seemed permanent. Some planets fall inward, some collide, some survive around remnants, some escape and become dark wanderers between stars. As bound regions themselves thin, many of those wanderers may eventually cross distances where another close gravitational encounter becomes effectively impossible. By then, the universe contains an enormous population of objects whose histories were written during the stellar age but whose futures unfold almost without light. They are remnants around remnants, surviving evidence of a time when stars still provided warmth, chemical disequilibrium, and regular cycles of change. Their cold endurance can last astonishingly long, but it does not answer the deeper question beginning to emerge beneath every solid surface and every compact core. Once stars are gone and planetary systems have scattered, the next uncertainty is no longer where matter will travel. It is whether matter itself is allowed to last. The question of whether matter survives forever begins with a particle that appears almost impossibly ordinary. The proton sits inside the nuclei of nearly every atom in planets, stars, dust, and living chemistry, carrying positive electric charge and contributing most of the mass of ordinary atomic matter. In every experiment so far, the proton has behaved as though it is stable. No confirmed proton decay event has ever been observed. That simple fact places a remarkable uncertainty beneath the entire far future of the universe. Because some theories extending beyond the standard model of particle physics predict that protons may eventually decay. While the standard model itself does not require such decay to occur, the difference between those possibilities is almost invisible on human timescales and enormous on cosmic ones. If the proton is truly permanent, then cold planets, stellar remnants, and other structures made from ordinary matter can remain physically intact for far longer than they would if their constituent particles slowly transform. If proton decay exists, then the universe does not merely lose stars and warmth. Over sufficiently long spans, it begins losing the ordinary material from which those objects are built. The reason proton decay appears in some theories comes from an attempt to connect forces that are separate in the standard model. At accessible energies, electromagnetism, the weak nuclear interaction, and the strong nuclear interaction have different strengths and behaviors. Some proposed grand unified theories suggest that at enormously higher energies, these interactions may emerge from a more unified description. In such models, processes forbidden or effectively absent at lower energies can become possible in principle, including transformations that do not preserve the number of baryons in the familiar way. Protons and neutrons belong to the family of particles called baryons, and ordinary nuclei depend on them. If baryon number is not an absolute conservation law, a proton could have an immense but finite lifetime. That does not mean it would carry an internal clock and decay at a predictable age. Radioactive processes are probabilistic. A population of unstable particles follows a statistical lifetime, with individual decay events occurring unpredictably. For a particle as apparently stable as the proton, that lifetime would have to be extraordinary, because experiments have watched enormous numbers of protons without detecting a convincing decay signal. The absence of detection does not prove immortality. It establishes that if decay occurs through the channels being searched for, it must be exceedingly rare. This is why enormous underground detectors can be used to look for an event that may never happen during the operation of the instrument. Large volumes of material contain vast numbers of protons, and the detector watches for combinations of particles that would match a predicted decay signature, while shielding itself as much as possible from cosmic rays and other backgrounds. A successful detection would alter more than particle physics. It would place an eventual expiration date, statistical rather than individual, on almost every familiar structure made from baryonic matter. A cold planet drifting between galaxies might appear unchanged for ages, but its nuclei would no longer be fundamentally permanent. One proton would decay, then another somewhere else, with intervals that remain enormous on ordinary scales. Across enough time, however, rare events accumulate. Atomic nuclei would be disrupted as their constituent baryons disappeared or transformed. The chemistry that once defined rock, ice, metal, and gas would become impossible to preserve indefinitely. White dwarfs and hypothetical black dwarfs would also be affected because their density does not protect them from a process rooted in particle stability itself. Their atoms are compressed and altered by stellar evolution, but they still depend on baryonic matter. If that matter is unstable, gravitational and quantum support can preserve the arrangement only while enough material remains to sustain it. The object would gradually lose mass and internal structure as decay products escaped or redistributed energy. The transformation would not resemble an explosion in the ordinary sense. The timescale would be too extended, and the environment would already be too cold and sparse. It would be more like a nearly imperceptible erosion occurring from within the matter itself. Neutron stars present a more complicated case, because their interiors contain matter at extreme density, where the simple picture of isolated protons inside ordinary nuclei no longer applies. Yet they too are largely baryonic objects. If the underlying theory permits processes that violate baryon number under the conditions present there, their ultimate persistence could be affected. The exact path would depend on particle physics that is not established, making detailed predictions far less secure than the broad statement that unstable baryonic matter cannot remain unchanged forever. That uncertainty is important. Far future cosmology often appears to offer precise sequences across unimaginable spans, but the farther the timeline is extended, the more it encounters questions that current experiments have not answered. Proton decay is one of the clearest boundaries between robust extrapolation and theoretical possibility. Stellar evolution is observed directly in many stages. White dwarf cooling is observed. Gravitational scattering is grounded in well-tested dynamics. Proton decay remains hypothetical. It belongs in the story because its existence would radically alter the fate of matter, not because it has been established. If protons are stable, the future opens along a different path. Cold planets, brown dwarfs, white dwarfs, and other remnants could remain as bound assemblies of ordinary particles for fantastically long periods. They would still face gravitational encounters, collisions, capture by black holes, and other rare processes. Quantum mechanics may also allow extraordinarily slow transformations in some objects under certain assumptions, but there would be no general mechanism forcing every piece of baryonic matter to dissolve simply because enough time had passed. The universe could retain dark, inert structures long after every ordinary source of starlight had vanished. A black dwarf in such a cosmos might remain as an almost perfectly cold relic, not truly eternal in any proven sense, but no longer carrying an obvious internal route toward disappearance. A planet cast into intergalactic space might continue orbiting nothing at all, its motion changing only through the expansion of the larger universe and the exceedingly rare chance of an encounter. Matter would become persistent even as activity became scarce. If proton decay does occur, the distinction between object and radiation gradually weakens. The organized mass locked into planets and stellar remnants would be converted into lighter products that can escape, scatter, or join the increasingly dilute background of particles and radiation. Structures maintained by electromagnetic bonds and ordinary nuclear matter would lose the constituents that make those bonds meaningful. The cosmos would become less populated not only because objects drift apart, but because many objects would cease to remain objects at all. Their mass energy would not simply vanish. It would be redistributed into forms far less capable of rebuilding the dense structures from which it came. This continues the thermodynamic direction already visible in the death of stars. Concentrated matter carries possibilities for interaction. Dilute low-energy particles spread through expanding space carry fewer opportunities to create large, organized systems. Proton decay, if real, would accelerate that movement from structure toward dispersion. Yet one class of object would remain fundamentally different. Black holes do not depend on the long-term stability of ordinary matter once material has crossed their event horizons. A black hole is characterized externally by properties such as mass, angular momentum, and electric charge, not by whether the matter that formed it once consisted of protons, iron nuclei, or collapsed stellar plasma. If baryonic structures outside black holes gradually disappear, the black holes already present can still persist. Matter may also fall into them before it has time to decay, adding to their mass and removing that material from the ordinary remnant population. In a universe where proton decay eventually erases planets and dead stars, black holes therefore become even more conspicuous by survival rather than by light. They may be surrounded by almost nothing, separated by immense expanding distances, and deprived of the bright accretion flows that once revealed their presence. Still, they remain massive distortions of space-time after most ordinary structures have faded. Whether protons live forever or not, the stellar era has already ended by this stage. The question of proton stability determines how much material architecture remains outside the black holes, but it does not restore the vanished stars. One branch leaves a universe containing cold relics alongside compact gravitational objects. The other gradually removes much of that relic population and replaces it with lighter particles and radiation. Both paths lead toward increasing darkness and isolation, but they reach that darkness through different inventories of what survives. The uncertainty is therefore not a small technical detail buried inside particle theory. It determines whether the distant universe remains filled with silent matter or whether even that silence is slowly dismantled. Beyond either possibility, however, the most durable large structures still waiting in the cosmic timeline are black holes, and once ordinary matter has lost its central role, their extraordinarily long reign can begin. The black hole era begins not with a sudden transition, but with a change in what remains capable of lasting. By this stage, ordinary star formation has ended. The final long-lived stars have exhausted their fuel, and many planetary systems have either dispersed or settled into cold, inactive arrangements. Depending on whether protons decay, much of the ordinary matter outside compact objects may also be slowly disappearing. Against that increasingly empty background, black holes become the dominant large concentrations of mass not because they are active, but because almost everything else has become less durable. A stellar black hole may have begun billions or trillions of years earlier as the collapsed core of a massive star. A supermassive black hole may have grown through accretion, mergers, and the long history of a galaxy. In the bright universe, both kinds were embedded inside busy environments filled with stars, gas, radiation, and repeated encounters. In the far future, those surroundings have thinned. The black holes remain while the structures that once made them visible have largely faded. Their survival changes the character of cosmic darkness. A black hole is not simply an object that emits no light. It is a region where gravity has become strong enough that, beyond the event horizon, paths leading outward no longer return to the external universe. The event horizon is not a material surface. It is a boundary in space-time, defined by what can and cannot escape. From outside, the black hole can be described by a small set of measurable properties such as mass, angular momentum, and electric charge. The complex details of the matter that formed it are hidden behind the horizon. This simplicity gives black holes an unusual kind of persistence. A white dwarf continues to cool, a planet can be scattered, a neutron star can lose rotational energy. Ordinary matter may decay if baryon number is not absolutely conserved. A black hole, by contrast, can remain almost unchanged for enormous intervals when little matter is available to fall into it. Its mass and spin may evolve only through rare mergers, the capture of stray particles, and the extremely slow quantum process associated with Hawking radiation. Before that radiation becomes important, the black hole can spend ages in near isolation. The scale of that isolation matters. During the stellar era, black holes and galaxies can encounter stars, gas clouds, and one another because the surrounding systems remain relatively dense. As galaxies age, repeated gravitational interactions slowly rearrange their contents. Some stars and remnants gain enough energy to escape. Others lose energy and move inward. Central black holes can grow through mergers when their host galaxies combine. And smaller black holes may eventually sink toward dense central regions through gravitational interactions with surrounding matter over immense timescales. A bound galactic remnant can therefore become less like a luminous galaxy and more like a sparse gravitational system dominated by compact objects, with a massive black hole near its center and a dwindling population of remnants around it. Yet even this arrangement does not remain busy forever. Every ejection reduces the number of possible future encounters. Every merger reduces the number of separate objects. Every expansion in the spacing between survivors lengthens the waiting time before the next significant event. The black hole era is defined as much by the intervals between events as by the events themselves. A collision that would seem impossibly rare in the present universe can still occur if there are enough opportunities spread across enough time. But as the universe becomes more dilute, even those opportunities decline. Some black holes may remain gravitationally bound in ancient systems. Others may be ejected through multi-body interactions or the recoil produced by asymmetric black hole mergers. Once expelled into intergalactic space, a black hole can become almost perfectly isolated, moving through a region with so little surrounding matter that meaningful accretion nearly stops. It may travel for spans far longer than the age of the present universe without encountering anything substantial. In such conditions, the familiar image of a black hole consuming its surroundings no longer applies. There may be almost nothing left nearby to consume. The most enduring black holes are therefore not necessarily the most active. Their longevity comes from the absence of change. Supermassive black holes occupy a special place in this future because larger black holes evaporate more slowly than smaller ones. The relation between mass and Hawking evaporation is deeply counterintuitive. A more massive black hole has a lower Hawking temperature and loses energy more slowly. So the giants that once sat in galactic centers can persist long after stellar mass black holes have entered later stages of their evolution. Before evaporation dominates, these central black holes may also grow by absorbing surviving stars, compact remnants, dark matter particles if suitable trajectories bring them inward, or other black holes. Yet the supply diminishes with time. Accretion becomes sporadic, then negligible. The black hole that once anchored a luminous galactic nucleus can spend its final vast epoch surrounded not by a blazing disk, but by darkness. This is one of the strongest reversals in the history of structure. In the young and middle-aged universe, the environments around feeding black holes can outshine entire galaxies. In the black hole era, the black holes themselves remain while the luminous evidence of their feeding history disappears. Their gravity persists after their spectacle is gone. If proton decay occurs, the contrast becomes sharper. Planets, white dwarfs, and other baryonic relics can slowly dissolve into lighter particles, while black holes continue to hold mass behind event horizons. Some decay products may escape into space, and some may eventually be captured, but the general population of solid and stellar remnants declines. If protons are stable, the universe retains more cold matter. Yet black holes still stand apart because of the timescales associated with their ultimate evolution. In either branch, they become among the last major reservoirs where large amounts of mass remain concentrated in one place. Concentration matters because the rest of the cosmos is moving toward dispersion. Radiation stretches to longer wavelengths. Free particles become more widely separated. Bound systems lose members. Temperature differences diminish. Against that trend, a black hole preserves an extreme concentration of energy and curvature even when its surroundings have almost completely thinned away. Yet this apparent durability has a limit. Classical general relativity by itself suggests that once a black hole forms, the event horizon can persist indefinitely unless the hole interacts with something external. Quantum field theory in curved spacetime changes that conclusion. Hawking's calculation shows that a black hole should possess a temperature and emit thermal radiation. For large astrophysical black holes, that temperature is extraordinarily low, which is why Hawking radiation is irrelevant to their present-day mass loss. Today, black holes exist in a universe filled with radiation and matter, and they can absorb more energy from their surroundings than they lose through this faint quantum emission. The balance changes only after the universe has cooled sufficiently. As the cosmic background radiation stretches and weakens, the environment eventually becomes colder than the black hole's effective Hawking temperature from that point onward. An isolated black hole loses more energy than it gains. The process is still extraordinarily slow, especially for massive black holes, but the direction has changed permanently. The beginning of net evaporation marks a threshold inside the black hole era. Until then, black holes are almost static survivors. Afterward, even the most durable structures in the universe carry a finite route toward disappearance. This is why their reign can be extraordinarily long without being eternal. They occupy the last great interval in which the universe still contains familiar macroscopic objects with enormous concentrated mass. Their horizons can survive after stars, planets, and galaxies have ceased to function as recognizable luminous systems. For stretches of time that overwhelm every earlier cosmic epoch, the main remaining structures may simply be black holes separated by expanding darkness, occasionally merging, occasionally capturing a stray particle, but more often doing almost nothing at all. The universe has not yet reached heat death, because these objects still represent concentrated energy, and because their eventual evaporation can release radiation into their surroundings. But the range of possible activity has narrowed dramatically. Almost every earlier engine of change has shut down. What remains is gravity, horizons, and the slow quantum leakage that finally places even black holes under the same rule that has governed the rest of cosmic history. Persistence is not the same as permanence. Their era is the longest shadow cast by the age of structure, and its end begins with a radiation so faint that for most of cosmic time it scarcely matters at all. According to semi-classical physics, a black hole is not completely black. Quantum fields near the event horizon give it a temperature, and that temperature allows the hole to emit what is now called Hawking radiation. For the black holes that exist in the present universe, the effect is almost unimaginably weak. A black hole with roughly the mass of the Sun has a Hawking temperature far below the temperature of the cosmic microwave background, so it absorbs more energy from its environment than it loses through quantum emission. The universe around it is still too warm. Matter, photons, and other forms of radiation continue to fall inward, and even an isolated black hole sits inside a background that overwhelms its own faint thermal output. That balance does not last forever. As cosmic expansion stretches the background radiation to longer wavelengths and lowers its temperature, the environment becomes progressively colder. Eventually, a black hole can find itself hotter than the space around it. From that point onward, the direction of the energy flow reverses. The hole still absorbs anything that reaches it, but in an increasingly empty universe, there is less and less available to fall in. While Hawking radiation continues, net mass loss begins, and the black hole enters an evaporation process that may last longer than almost every other familiar physical era combined. Hawking radiation arises from the interaction between quantum theory and curved spacetime. It is often described using pairs of particles appearing near the horizon, with one escaping and the other falling inward. But that picture is only a simplified analogy. The more precise statement is that the definition of particles depends on the structure of spacetime and on the observer, and a black hole horizon changes the quantum fields in such a way that distant observers detect thermal radiation. The energy carried away by that radiation must come from the mass of the black hole. As energy leaves, the hole becomes lighter. That loss is extremely slow for large black holes because Hawking temperature decreases as mass increases. A stellar mass black hole is colder than almost any natural environment now known, while a supermassive black hole is colder still. This inverse relationship gives the far future an unexpected hierarchy. The smallest surviving black holes evaporate before the largest ones, and the giants that once occupied galactic centers become some of the final macroscopic structures left in the universe. A black hole with approximately the mass of the Sun would require a timescale of roughly 10 to the 64th years to evaporate if it remained isolated, and if the semi-classical calculation continues to apply throughout the process. A much more massive black hole lasts vastly longer. These durations are so far beyond the present age of the universe that ordinary comparisons stop being useful. Stellar evolution, planetary cooling, and even the era of long-lived red dwarfs occupy only an early prelude beside them. Yet the immense duration does not change the direction of the process. Once a black hole is losing more energy than it receives, its mass gradually declines. As the mass falls, its temperature rises. As its temperature rises, its radiation becomes stronger. The evaporation therefore accelerates. For most of its lifetime, the black hole changes almost imperceptibly, losing mass at an extraordinarily low rate. Near the end, the situation becomes very different. A smaller black hole is hotter and radiates more powerfully, so each stage of mass loss makes the next stage proceed faster. The long quiet decline eventually gives way to a much shorter final phase in which the remaining mass is converted into increasingly energetic radiation. Exactly what happens at the very end is not known with complete confidence, because the calculation reaches a regime where quantum gravity should become important, and no experimentally confirmed theory of quantum gravity yet provides a complete description. Semi-classical physics predicts continued evaporation, but it cannot by itself settle whether the process ends in total disappearance, a tiny stable remnant, or some other behavior produced by deeper physics. That uncertainty is small in duration compared with the almost endless evaporation that comes before it, but conceptually, it is one of the largest unanswered questions in the story. The fate of information adds another layer. In ordinary quantum mechanics, information about a physical state is not expected simply to vanish. A black hole appears to hide the detailed information carried by the matter that crossed its horizon. While Hawking radiation in the simplest calculation looks thermal and apparently unrelated to those details, if the black hole then evaporates completely, the question becomes whether the information is somehow encoded in subtle correlations within the radiation, preserved in an unseen remnant, or lost in a way that would require a fundamental change in quantum theory. This is the black hole information problem, and it shows that black hole evaporation is not merely a distant astronomical curiosity. It sits at the meeting point of gravity, thermodynamics, quantum mechanics, and the structure of space-time itself. The far future of the universe therefore depends on physics that is already difficult to reconcile in the present. Even without a final theory, however, the broad energetic consequence remains clear within the semi-classical picture. Black holes that once acted as sinks for matter eventually become sources of radiation. Matter falls in during the earlier universe, disappears behind horizons, contributes to black hole mass, and then, over extraordinary time scales, that stored mass is returned to the exterior in an altered form. The release is not a reconstruction of the original stars, planets, gas clouds, or particles. The organized structures that entered the holes do not simply emerge again as recognizable objects. What returns is radiation distributed into an environment that has become colder, larger, and more dilute. Concentrated mass is converted into increasingly dispersed energy. This makes black hole evaporation another step in the general movement from structure toward thermodynamic simplicity. The process also changes the meaning of darkness. During most of the black hole era, the universe is dark because the dominant surviving objects emit almost nothing detectable. Yet Hawking radiation means that the darkness is never perfect. Every black hole carries a temperature, however low, and everyone slowly leaks energy into space once its surroundings are cold enough. The universe may contain almost no stars, almost no active galaxies, and perhaps little surviving baryonic matter, but the remaining black holes still generate a faint background of particles and radiation. Those emissions are separated by enormous distances and stretched further by expansion. They do not restore a bright cosmos, They simply prevent the black hole era from being absolutely static. Over time, smaller holes vanish and the population shifts toward larger ones. Stellar mass black holes disappear long before the most massive galactic remnants. Intermediate mass holes follow on their own longer schedules. Supermassive black holes, carrying millions or billions of stellar masses or more, can dominate the final stages because their low temperatures make their evaporation extraordinarily slow. A universe that once contained countless luminous galaxies may eventually be reduced to widely separated horizons, each surrounded by an almost empty region, and each losing mass so slowly that meaningful change is nearly impossible to detect over any ordinary interval. Still, the change continues. One by one, those horizons shrink, their temperatures rise, their remaining lifetimes shorten. The black hole population becomes smaller in number as the universe grows larger in scale. When only the most massive survivors remain, there may be no other structures of comparable significance anywhere within causal reach. Their eventual disappearance marks a threshold more complete than the death of the last star, because stars leave compact remnants behind, while evaporating black holes may leave only radiation and whatever unknown physics governs their final moments. The universe does not become nothing when the last horizon is gone. Energy remains, particles remain, expansion continues, but the last major reservoirs of concentrated gravitational mass have been dismantled. What follows is a cosmos in which structure is no longer merely rare. On the larger scales that remain physically relevant, it may have almost entirely surrendered to dispersion. When the final black hole disappears, the universe crosses into a state with no remaining structure remotely comparable to the great concentrations of mass that shaped earlier cosmic history. There are no ordinary stars burning through nuclear fuel, no active galaxies fed by cold gas, and no large black holes holding matter behind event horizons. What remains depends in part on unresolved questions such as proton stability and the ultimate details of black hole evaporation. But the broad picture is one of extraordinary dilution, photons, neutrinos, electrons and positrons where they survive, possible dark matter particles, and other low-energy remnants move through an expanding cosmos in which encounters become increasingly rare. The universe is not empty. It is populated by things that have almost nothing left to do to one another. That distinction matters because emptiness and inactivity are not the same physical condition. A perfectly empty universe would contain no matter or radiation at all. The far future envisioned in the heat-death picture can still contain particles and fields, yet they are spread so thinly and with so little usable contrast that large-scale processes can no longer organize them into stars, planets, or anything resembling the structures of the present age. The disappearance of the last black hole therefore removes the final great reservoir of concentrated gravitational energy, but it does not erase energy itself. Hawking radiation has returned that mass to the surrounding universe in a dispersed form. The photons and other particles produced during evaporation continue outward, their wavelengths stretched by cosmic expansion. As space grows, their energy falls. A universe once capable of concentrating gas into blazing stars now carries much of its surviving energy in radiation, so weak and sparse that individual quanta may travel across enormous distances without interaction. The scale of separation becomes one of the defining facts of the era. Earlier cosmic history was full of collisions, captures, mergers, shocks, nuclear reactions, and gravitational collapse. Even when those events were uncommon in any particular location, the universe contained enough dense environments for them to be ordinary somewhere. In the post-black hole future, density has fallen so far that the waiting time between meaningful interactions can exceed almost any timescale associated with the structures that came before. A particle may cross an expanding region without ever encountering another particle in a way that changes either one significantly. Radiation passes through space with fewer absorbers available to capture it. Gravitational clumping becomes ineffective where no sufficiently dense concentrations remain. The cosmos still evolves, but much of that evolution is simply the continued redshifting and separation of what is already there. Expansion does not destroy a photon, yet it changes the photon's energy as its wavelength lengthens with the scale of the universe. Over enough time, radiation that was once energetic becomes progressively softer. The background produced by countless earlier processes, from stellar light to black hole evaporation, is stretched toward lower and lower frequencies. If dark energy remains close to a cosmological constant, accelerated expansion continues during this entire period, increasing the distance between regions that are not bound and reinforcing causal isolation. The remnants of past events are therefore not merely faint, they are being carried into a geometry that makes future interaction still less likely. This changes what it means for the universe to contain energy. Energy can be present while being almost impossible to exploit. A hot region beside a cold one can drive processes because energy flows down the difference between them. Dense matter beside empty space can collapse, radiate, or rearrange itself. Chemical systems can perform work because concentrations differ and reactions can proceed toward more probable states. The late universe has spent an immense history reducing such contrasts. Stars converted nuclear fuel into radiation. Radiation spread outward. Matter collected into remnants. Remnants cooled or decayed. Black holes concentrated mass for enormous spans and then, within the semi-classical picture, returned that mass through Hawking emission. At every stage, local complexity could survive for a time because some difference remained available to drive change. After the final black hole, the number of such differences has become very small. This does not require every point in space to have exactly the same temperature, or every particle to carry exactly the same energy. Heat death is not a claim of perfect uniformity in every microscopic detail. It is a statement about the disappearance of accessible free energy on large scales. Small fluctuations can remain. Quantum fields need not become literally featureless. Individual particles can still move, scatter, or fluctuate according to the laws that govern them. What disappears is the rich hierarchy of organized structures that once made those microscopic events consequential. A rare collision between two low-energy particles does not rebuild a galaxy. A weak photon crossing an empty horizon does not restart stellar nucleosynthesis. The physical rules continue to operate, but the initial conditions required for large new structures are no longer available in the same way. Some uncertainties remain especially important here. If dark matter is made of stable particles, then those particles may continue to populate the universe long after baryonic structures are gone. If dark matter particles can decay or annihilate, the inventory changes. If protons are stable, cold remnants of ordinary matter may persist much longer than in a universe where proton decay occurs, meaning that the transition to an almost purely radiative state is less complete. If the final phase of black hole evaporation leaves stable remnants rather than ending in total disappearance, those remnants could also survive. None of these possibilities restores the universe to its earlier condition. They affect what kinds of relics remain, not the overall loss of cosmic activity. The trend toward greater dilution and weaker gradients survives across many versions of the scenario. Even gravity becomes less visually important once there are no large concentrations left to shape recognizable systems. Gravity still exists, but its effects are determined by what mass and energy remain available to curve spacetime. Widely separated particles exert gravitational influence in principle. Yet accelerated expansion can prevent remote regions from ever gathering together again. Local attraction cannot easily reconstruct structure if the ingredients are already separated beyond causal reach. In that sense, expansion and thermodynamics reinforce one another. Expansion increases separation and stretches radiation, while thermodynamic evolution reduces the useful contrasts that once powered complex processes. The universe approaches a condition where almost every path leads toward less interaction rather than more. There is a profound difference between this state and a destructive ending. Nothing needs to explode, nothing needs to erase space-time. The final black hole can vanish into radiation, and after that the universe can simply continue. The laws of physics do not need to stop. Space can keep expanding. Quantum fields can remain. Particles can persist according to whatever lifetimes their underlying physics allows. Yet the cosmos can still be considered effectively dead, because the mechanisms that once generated new, organized complexity have nearly all disappeared. The word effectively is important. It avoids claiming an absolute cessation that physics may not justify. Extremely rare events may still occur. Quantum fluctuations may still exist. Unknown physics could alter the story at scales or durations beyond established theory. But within the heat-death framework, none of those possibilities presently provides a known route back to a universe rich in sustained structure. The final black hole therefore marks a transition from a cosmos where at least a few large engines of change remain to one dominated by passive dilution. Before its evaporation, a black hole still contains concentrated mass and a finite temperature. Its shrinking horizon is still a dynamic system. After it is gone, the remaining radiation joins everything else already spreading through the expanding universe. No successor structure naturally takes its place. The hierarchy of galaxies, stars, planets, remnants, and horizons has been reduced to an almost structureless background. What remains is not nothingness, but the aftermath of every earlier concentration having been spent. This is the threshold at which the physical idea of heat death becomes unavoidable, because the central question is no longer what objects survive. It is whether any meaningful energy gradient survives with them. Heat death is not a final explosion, a collapse, or a moment when the universe runs out of energy. It is the name given to a limit in which energy still exists but is distributed so evenly, and useful differences have become so weak that almost no large-scale process can continue to extract work from them. The idea comes from thermodynamics, where the direction of change is closely tied to entropy. Entropy is often reduced to the word disorder, but that description is too vague for the far future of the cosmos. A more useful way to understand it is through the number of microscopic arrangements compatible with a given macroscopic state, and through the tendency of isolated systems to evolve towards states that are more statistically probable. In practice, those states usually spread energy out. A hot object cools in a colder environment because energy flows from the temperature difference. Gas expands into available volume because there are overwhelmingly more ways for its particles to be dispersed than confined to one small region. A star can shine because its interior contains conditions very different from the space around it. Life, chemistry, weather, geological activity, and almost every complex process depend on similar contrasts. Heat death describes a future in which those contrasts have been reduced until there is little left for physical systems to exploit. The universe can therefore be cold without being literally at absolute zero, and it can be full of energy without that energy being useful in the ordinary thermodynamic sense. That distinction is the heart of the scenario. During earlier cosmic eras, energy is repeatedly concentrated and released. Gravity pulls gas into stars, Nuclear fusion converts mass into radiation. Supernovae scatter heavy elements. Galaxies merge. Planets cool. Black holes absorb matter and over far longer times. May return mass through Hawking radiation. Each event changes the form and location of energy while increasing the overall thermodynamic tendency toward more probable states. Local decreases in entropy can occur, but they require larger increases elsewhere. A forming star creates an organized, dense object, yet the collapse releases heat and radiation into the surrounding universe. A living system can maintain intricate structure, but only by consuming free energy and exporting entropy to its environment. Complexity is therefore not a violation of thermodynamics. It is something that can arise temporarily where strong gradients exist. The far future becomes hostile to complexity not because the laws suddenly forbid organization, but because the gradients that make sustained organization possible become increasingly unavailable. By the time black holes have evaporated, much of the history that once created steep differences in temperature, density, and chemical potential has already played itself out. Radiation has been stretched, matter has been dispersed, decayed, or locked into relics depending on the underlying physics. Bound systems have thinned. The remaining universe is larger, colder, and less structured. Heat death is the continuation of that trend rather than a separate event added at the end. In a universe whose accelerated expansion persists, distant regions move beyond causal contact, while any freely propagating radiation is redshifted toward lower energy. If a cosmological constant remains the dominant large-scale component, the universe approaches a future in which ordinary matter and radiation become ever less significant to the total energy budget, even though they do not necessarily disappear at once. The thermodynamic story then becomes unusual, because cosmic expansion itself shapes what equilibrium can mean. A simple box of gas reaches equilibrium inside a fixed container. The universe has no external container, and its geometry continues changing. For that reason, heat death should not be pictured as every particle eventually sitting in one perfectly uniform soup at one fixed temperature. The real cosmological situation is more subtle. Horizons, quantum fields, gravitational degrees of freedom, and the expansion of space-time complicate any exact definition of maximum entropy for the entire universe. Yet the physical intuition remains robust. Accessible free energy declines, macroscopic gradients weaken, and the number of processes capable of producing sustained structure becomes smaller. The phrase Big Freeze emphasizes another side of the same broad future. As expansion continues, radiation cools and matter becomes more isolated. The cosmic environment trends toward extraordinarily low temperatures and densities. Heat death emphasizes the loss of usable thermodynamic contrast. The two ideas are often discussed together because continued accelerated expansion naturally drives both. A cold universe is not automatically in heat death if strong gradients remain somewhere, and a system can approach thermodynamic equilibrium without every component being literally frozen. Still, in the long-term scenario considered here, the cooling and the thermodynamic flattening reinforce each other. The universe becomes colder because radiation is diluted and redshifted, and it becomes less capable of useful work because sources of concentrated energy have disappeared. There is also an important difference between high entropy and inactivity. Entropy does not mean that particles stop moving. Even in thermal equilibrium, microscopic activity can continue. Particles can possess momentum. Quantum fields can fluctuate. Radiation can propagate. Rare interactions can occur. What changes is the ability of those events to generate persistent macroscopic direction. If every accessible part of a system is already near the same thermodynamic condition, there is no dependable downhill path for energy to follow that could power a machine, maintain a metabolism, drive a storm, or ignite a star. Motion remains, but organized throughput disappears. The universe becomes dynamic in the smallest sense while becoming nearly static in the sense that matters for complex structure. This is why heat death is sometimes described as the state of maximum entropy. Although the cosmological wording should be used with care, for an ordinary isolated system of fixed energy and volume, equilibrium corresponds to the overwhelmingly most probable macrostate, and therefore to maximum entropy under those constraints. The universe is expanding and contains gravity, so its total entropy bookkeeping is more complicated. Black holes themselves carry enormous entropy, which is one reason they matter so much in discussions of the remote future, when they eventually evaporate. The entropy associated with their mass is transferred into radiation and other products. The details connect gravity, quantum theory, and thermodynamics in ways that are still not fully understood. Even so, nothing in the standard heat-death picture requires entropy to become a perfectly simple number that stops changing forever at a sharply defined instant. It is enough that the universe approaches a condition in which no large reservoir of low-entropy free energy remains available to support complex processes. That approach can be endless. The final state may never arrive as a completed moment in finite time. Instead, each later epoch can be colder, more dilute, and less active than the one before it. This gives heat death a peculiar relationship with the idea of an ending. A supernova ends when the explosion and collapse produce a new remnant. A star ends when sustained fusion ceases. A black hole, within the semi-classical picture, ends when evaporation removes its horizon. Heat death has no equally clean boundary. There may be no last thermodynamic event after which nothing else can ever happen. There can always be another photon travelling through empty space, another fluctuation, another extremely rare interaction, or another change permitted by whatever stable particles and fields remain. The relevant difference is that these events do not rebuild the gradients that the universe has spent its history exhausting. They are isolated motions inside a state with almost no capacity for cumulative complexity. Even the word death can therefore mislead. The universe is not dead in the biological sense, and physics has not ceased. It is closer to a system that has lost almost every accessible source of disequilibrium. The equations still describe fields and particles, space-time still has geometry, expansion still has a history. What has largely vanished is the contrast that once turned those ingredients into galaxies, stars, chemistry, and continuous chains of change. A photon can exist without a star to absorb it. A particle can persist without ever meeting another. Energy can remain without gathering into a reservoir from which useful work can be extracted. Heat death is not nothingness. It is existence stripped of almost all thermodynamic leverage. That is why it stands as the most gradual of cosmic endings. The universe does not disappear. It does not have to tear itself apart or reverse into collapse. It simply continues to spend the differences that made earlier epochs active. As those differences approach irrelevance, the remaining question becomes more difficult than the fate of any object. If events become vanishingly rare and no macroscopic process remains to mark regular change, then time itself still appears in the equations, but the physical meaning of a clock becomes hard to anchor. The next boundary is therefore not between something and nothing. It is between a universe that changes richly and one in which change has almost lost its scale. Time remains in the equations even after almost every familiar clock has disappeared. That separation between mathematical time and physical time becomes especially important in a universe approaching heat death, because the passage of time is usually recognized through change. A clock does not measure an invisible substance flowing past it. It compares one physical process with another: the swing of a pendulum, the vibration of an atom, the rotation of a planet, the pulse of a star, and the decay of an unstable particle can all serve as clocks because each provides a sequence of distinguishable states. In the present universe, there is no shortage of such sequences. Stars evolve, galaxies move, planets orbit, atoms transition between energy levels, and radiation carries information from one event to another. Time is woven into a cosmos full of processes. In the distant heat-death future, the equations may still allow a time coordinate, but the physical universe offers fewer and fewer events capable of marking its passage in any useful macroscopic way. That does not mean time suddenly stops. It means the distinction between one late epoch and another becomes increasingly difficult to anchor to change that matters. If two moments contain almost exactly the same large-scale conditions, with no stars igniting, no planets warming, no black holes shrinking, and no strong energy gradients driving activity, then the universe can continue to age without developing a rich new history. The idea is subtle because ordinary experience treats time and change as inseparable. A day is recognized through motion in the sky and cycles in biological systems. A year is tied to an orbit. Geological time is reconstructed through layers, erosion, decay, and the transformation of environments. Cosmic time is inferred through expansion, stellar evolution, and the changing temperature and density of the universe. Every practical measure of duration relies on something happening. Remove enough processes, and the equations can remain while the operational meaning of a clock grows thinner. Even so, perfect stillness is not required by the heat-death picture. Individual particles can continue moving, radiation can continue propagating, quantum fields can remain present. Rare interactions may still occur if particles happen to meet. The universe can therefore contain events in a minimal sense, while lacking the dense succession of events that makes earlier eras easy to divide into chapters. The difference is one of scale and consequence. A single low-energy particle crossing an enormous empty region can mark change, but it does not create a new thermodynamic era. A weak interaction between isolated particles may alter their states, but it does not rebuild a star, a galaxy, or a sustained source of free energy. The late universe can remain active microscopically while becoming nearly featureless macroscopically. This creates an unusual asymmetry between time and history. Time can continue as a parameter describing evolution, while history becomes almost empty because there are so few distinctive transitions left to record. Earlier cosmic epochs are separated by major changes. The universe cools enough for atoms to form. Gravity builds stars and galaxies. Stellar populations mature. Star formation declines. Remnants dominate. Black holes eventually evaporate. Each transition gives the timeline a recognizable structure. Heat-death removes most of those landmarks. There may be no next dominant class of object, no new widespread source of energy, and no replacement for the structures that have disappeared. The future becomes less like a sequence of eras and more like a continuation of the same increasingly dilute condition. This is why the question of whether time still has meaning cannot be answered simply by saying that nothing happens. Something can still happen, but the events may become so rare and so disconnected that they no longer provide a practical framework comparable to clocks in the present universe. A clock requires not only change but a repeatable or at least ordered process. If the surviving cosmos is dominated by particles separated by immense distances, there may be very few naturally recurring macroscopic systems left. No stable day follows a planetary rotation if planets have vanished or become inert. No stellar lifetime can serve as a reference once stars are gone. No black hole evaporation can mark an era after the last horizon disappears. A future observer is not required for this problem to exist. The issue is physical before it is observational. The late universe itself contains fewer structures capable of generating regular cycles. In that sense, time remains describable while timekeeping becomes impoverished. Expansion can still provide one kind of large-scale change if accelerated expansion continues. Distances between unbound regions can increase, and wavelengths of freely traveling radiation can continue to stretch. The geometry of the universe therefore need not be static, even when local structure has nearly vanished. But expansion is not the same as a conventional clock. It can define an evolving background. Yet the ability to compare that evolution with local recurring processes becomes more limited as those local processes disappear. The universe may continue changing in its scale while becoming less eventful in almost every other sense. This distinction prevents heat death from turning into a frozen snapshot. The far future is not necessarily a single final frame. It can be an endless approach toward greater dilution, lower accessible energy, and weaker interaction, with each later interval differing from the previous one mainly by degree. That kind of future resists familiar language. Words such as before, after, duration, and event remain valid within physical descriptions, but their intuitive force comes from a world where things happen often enough to compare. In an almost changeless universe, the phrase "a long time" can become physically strange, long compared with what cycle, what decay, what orbit, or what transformation. If no robust macroscopic process remains, duration can still be represented mathematically, but fewer material systems exist to embody it. The question then shifts from whether time exists to whether time remains measurable in the same operational sense. Modern physics generally treats measurements as relationships between physical systems. A clock is one system used to track the evolution of another. If nearly every complex system has disappeared, the universe loses much of the infrastructure that makes such comparisons straightforward. This does not prove that time is unreal or that it ends at heat death. It shows that the physical meaning attached to time can depend on the availability of change. Heat death therefore pushes a familiar concept into an unfamiliar regime. The earlier universe contains so many processes that time feels unavoidable. The late universe may contain so few that time becomes more like a background parameter than a richly expressed dimension of experience and history. Even entropy, which gave the cosmos a strong thermodynamic direction, becomes less useful as a visible arrow once the universe has approached a state with almost no accessible gradients left. During active eras, the direction from lower entropy conditions toward higher entropy ones is written into cooling stars, spreading radiation, chemical reactions, and irreversible processes in the heat-death limit. Large additional changes in that direction become scarce. The arrow is not necessarily erased from the laws, but there is less remaining structure through which it can announce itself. A nearly equilibrium universe therefore does not merely lose energy gradients. It loses many of the macroscopic signs that distinguish a meaningful sequence of events. The most careful conclusion is not that time ceases, and not that the future becomes literally eventless. It is that the connection between time and observable physical change becomes progressively weaker as the universe approaches thermodynamic exhaustion. The equations can continue to order states. Expansion can continue. Particles can move. Fields can fluctuate. Yet the great clocks of cosmic history are gone one after another, and nothing comparably organized replaces them. In that setting, the word after begins to lose some of its ordinary force. There can always be a later state. But the later state may differ so little from the earlier one that calling it a new chapter adds almost nothing. The universe continues, but continuation is no longer the same thing as development. That is the quietest possibilities contained in heat death, not a final moment when time stops, but a future so sparse in consequential change that time survives mainly as the ordering of almost identical states. And once that possibility is understood, the next question opens in the opposite direction. If the heat-death future depends on accelerated expansion continuing in broadly the same way, then any change in the physics driving expansion could replace this almost timeless ending with something far more abrupt. Heat-death is the leading long-term picture only if the forces shaping cosmic expansion continue behaving roughly as they appear to behave now. That condition is easy to overlook because the distant future is often described as though it has already been selected. In reality, every prediction rests on assumptions about physics that remain incompletely understood, and dark energy carries the largest of those uncertainties. If its properties remain close to those of a cosmological constant, accelerated expansion can continue indefinitely, and the universe can drift toward the cold, sparse state already described. If dark energy evolves, however, the future may depart sharply from that path. Some possibilities replace the almost motionless ending of heat death with a much more dramatic transformation. Others return the universe toward high density. Still others do not depend on cosmic expansion at all, but on the possibility that the vacuum state underlying present physics is not absolutely stable. The Big Rip is one of the clearest examples of how a small change in theoretical assumptions can produce a completely different ending. It arises in models where the component driving acceleration behaves more extremely than a cosmological constant. In such a case, the effective dark energy density can increase as the universe expands rather than remaining constant. The expansion then accelerates ever more strongly. At first, the result resembles the more familiar future of cosmic isolation. Distant galaxies move beyond causal contact, and large-scale structure becomes increasingly separated. The difference appears when the accelerating expansion begins to compete with forces that normally keep smaller systems bound. Galaxy clusters can be pulled apart as the expansion between their members grows too strong for collective gravity to maintain the structure. Later, in sufficiently extreme versions of the scenario, individual galaxies can lose coherence. The process can continue towards smaller scales, potentially overcoming stellar systems and eventually forces holding matter together. The name Big Rip comes from this hierarchy of disruption, but the scenario should not be confused with a direct consequence of the acceleration already observed. Ordinary accelerated expansion does not automatically tear apart atoms, planets, or galaxies. The Big Rip requires a particular form of dark energy, whose behavior has not been established. It remains a theoretical branch, not a forecast supported at the same level as the observation that expansion is accelerating. Its scientific value lies partly in showing how strongly cosmic destiny depends on the equation describing dark energy. Change that equation, and the difference between eternal dilution and catastrophic disruption can become fundamental. The Big Crunch occupies nearly the opposite direction. Instead of expansion strengthening without limit, the universe eventually stops expanding and begins contracting. Matter that had been moving apart would find its separations decreasing on large scales. Radiation would be blue-shifted rather than red-shifted as the cosmic scale shrank. Temperatures and densities could rise. Structures might undergo repeated interactions as the available volume decreased, and the universe could move toward a state far denser than anything in its late expanding history. In older cosmological discussions, the Big Crunch was often linked directly to whether the universe contained enough matter for gravity to halt expansion. The modern picture does not reduce so simply to a balance between matter and outward motion, because dark energy plays a major role in the equations governing the expansion rate. With the currently favoured standard model and persistent accelerated expansion, a future recollapse is not the preferred outcome. A big crunch would require the large-scale dynamics to change, potentially through evolving dark energy or other physics not captured by the simplest model. The possibility is therefore not ruled out as a logical future of every imaginable cosmology, but it does not follow naturally from the present standard description. If some future theory allowed expansion to reverse, the contraction itself would raise new questions. It is tempting to imagine a shrinking universe simply running cosmic history backward, but thermodynamics prevents such a simple mirror image. Entropy accumulated during expansion would not automatically disappear. Stars would not neatly reassemble from remnants in reverse sequence, and radiation would not reconstruct every lost structure. A contracting universe would have its own evolution, shaped by rising density and temperature but still carrying the thermodynamic history of what came before. Where the contraction ends in a singular state, a transition, or something else depends on physics at energies where classical general relativity is expected to become incomplete. This is where ideas such as a cosmic bounce appear. Some speculative models propose that an extreme contraction could be followed by renewed expansion, avoiding an absolute beginning or ending and producing repeated cosmic phases. Other models imagine a bounce only once, with a previous contracting state giving rise to a new expanding universe. These ideas are scientifically interesting because they attempt to extend cosmology through regimes where familiar equations reach their limits, but they are not established descriptions of what will happen. They require assumptions about quantum gravity, matter, or space-time that have not been confirmed observationally. A bounce should therefore remain separated from the big crunch itself. Contraction can be discussed as one possible large-scale behaviour, while a rebound from that contraction belongs to a more speculative layer. Vacuum decay introduces an entirely different kind of ending, because it does not require the universe to wait for stars to die, black holes to evaporate, or expansion to reach any particular stage. In quantum field theory, what appears to be empty space is described by fields that possess particular states. The present vacuum may represent the lowest possible energy configuration of those fields, but some theoretical considerations allow another possibility: the current state could be metastable. A metastable vacuum is stable enough to persist for an extremely long time, while not being the true lowest energy state available. If that were the case, quantum processes could in principle allow a transition to a lower energy vacuum. Such a transition is often described as the nucleation of a bubble of the new vacuum. The interior of that region would have different field conditions, and the boundary could expand outward at a speed approaching that of light. The consequences inside the transformed region could be profound because particle properties, interaction strengths, or the structures permitted by physics might differ from those in the present vacuum. Ordinary atoms and chemistry might not survive the change, yet almost every statement about the detailed outcome carries uncertainty, because the lower vacuum state, if one exists at all, is unknown. Vacuum decay is therefore not a prediction that destruction is waiting somewhere beyond the visible sky. It is a theoretical possibility arising from questions about the stability of the quantum vacuum. There is also no established way to assign the universe a reliable countdown towards such an event using current knowledge. If the present vacuum is absolutely stable, the scenario never occurs. If it is metastable, its lifetime could be vastly longer than any ordinary cosmic timescale. The uncertainty is not a small error bar around a known date. It is uncertainty about whether the process is physically available at all. These alternative endings reveal a general pattern. The farther cosmology reaches into the future, the more the answer depends on theories that have been tested only under present or past conditions. Heat death follows naturally when observed. Accelerated expansion is extrapolated with dark energy, behaving approximately as a constant. The Big Rip requires a more extreme evolution of the component driving acceleration. The Big Crunch requires the large-scale expansion history to change enough for contraction to begin. Vacuum decay depends on the underlying quantum state of empty space being metastable. A cosmic bounce adds further assumptions about what happens when gravitational collapse reaches densities beyond the regime where known classical descriptions can be trusted. None of these possibilities belongs at the same level of confidence, and none should be presented as though the universe has already chosen among them in a way current observations can reveal. The value of considering them is not that one provides a more dramatic ending than another. Their value is that they expose which unknown pieces of physics actually control the answer. Dark energy determines whether expansion continues in its present form, weakens, strengthens, or reverses. Quantum field theory raises questions about whether the vacuum itself is permanent. Quantum gravity becomes unavoidable if contraction or extreme density drives space-time beyond the domain where general relativity can be used alone. The end of the universe is therefore connected directly to the unfinished foundations of modern physics. The more distant the forecast, the more clearly those unfinished foundations become visible. Heat death remains the calmest extrapolation of the standard picture, but it is not protected from revision by the fact that it lies far away. A future measurement showing that dark energy evolves could change the preferred trajectory long before the universe itself reaches any final stage. A deeper theory could show that the vacuum is absolutely stable, removing one class of endings, or reveal entirely different transitions that have not yet been imagined with confidence. Cosmic destiny is not only a problem of waiting long enough, it is a problem of understanding the laws well enough. And this leaves the final question in a more precise form. If no catastrophic alternative occurs, if expansion continues, if black holes evaporate, and if the universe approaches heat death, then there may still be no final boundary separating existence from what comes afterward. The deepest uncertainty is not merely which ending wins, but whether the concept of an afterward belongs to the universe at all. After heat death, there may be no next event waiting beyond the end. That possibility is difficult to express because ordinary language treats endings as boundaries. A star dies and leaves a remnant. A species disappears and the biosphere continues without it. A geological era closes and another follows. Even the evaporation of a black hole produces a later state containing the radiation that escaped from it. Heat death is different. If the universe approaches a condition in which usable energy gradients have almost vanished, matter and radiation have become extraordinarily dilute, and large-scale structure no longer forms, then the end is not followed by a new phase in the familiar sense. The same condition can simply continue. Expansion can persist. Radiation can become still more redshifted. Surviving particles can become more isolated. Rare interactions can occur without producing any sustained reversal of the overall thermodynamic direction. There is a later state, and then a later one beyond that, but each may contain less that distinguishes it from what came before. In this picture, the universe does not cross a final line. It approaches a future in which the concept of a meaningful afterward becomes progressively weaker. This is the simplest answer allowed by the heat death scenario, and also one of the least intuitive. Nothing new has to begin. A cold, dilute cosmos can continue indefinitely without transforming into another recognizable cosmic era. The mathematical description of space-time may extend onward, while the inventory of consequential events approaches almost nothing. That does not make the future literally empty of physics. Quantum fields remain part of the description. Whatever stable particles survive continue to possess states and interactions. If accelerated expansion persists, horizons remain important and distant regions become permanently disconnected. But none of these facts guarantees the emergence of a new structure comparable to stars, galaxies, or an early hot universe. Continuation alone does not imply renewal. This is where speculative cosmology begins to separate sharply from established extrapolation. There are ideas in which heat death is not the final word. Some propose cyclic behavior, in which the cosmos passes through repeated phases, rather than moving only once from a hot, dense beginning toward dilution. Others imagine a big bounce, where a prior period of contraction leads into expansion, potentially replacing a singular beginning with a transition. Still others explore whether quantum processes could generate new inflating regions of space-time, perhaps producing domains that evolve independently from the old universe. These possibilities arise from serious theoretical work, but they do not currently form a confirmed description of what follows heat death. They depend on assumptions about gravity, quantum fields, vacuum structure, or the global geometry of space-time that have not been tested in the regimes where the proposed transitions would occur. A cyclic universe, for example, faces the problem of explaining how entropy behaves from one cycle to another. If entropy simply accumulates, repeated cycles do not return naturally to identical beginnings. Some models attempt to avoid that difficulty through changes in geometry, expansion, or the way physical degrees of freedom are counted. But those solutions remain theoretical. A bounce faces a related challenge. General relativity can describe contraction toward extreme density, but once curvature and energy density approach regimes where quantum gravitational effects should dominate, the classical equations cannot be assumed to remain complete. A bounce, therefore, requires a theory capable of describing space-time under conditions that have never been directly observed. It is possible to construct models in which collapse turns into expansion, but possibility is not evidence that the actual universe will do so. The same caution applies to proposals in which new universes form through quantum processes. Quantum field theory allows fluctuations and tunneling phenomena, and inflationary cosmology has motivated ideas in which expanding regions can emerge under particular field conditions. Yet moving from those mathematical possibilities to the statement that a new universe will eventually arise after heat death is a step the evidence does not currently support. The far future may provide unlimited duration, but unlimited duration does not mean every imaginable event becomes inevitable. A process must first be physically allowed, and its probability must be meaningful within the correct theory. If the relevant process has exactly zero probability, no amount of time produces it. If the framework used to calculate the probability breaks down, the waiting time itself may not be well defined. This is one reason claims about what must happen after an infinite future require unusual care. The quantum vacuum deepens the uncertainty. Empty space in modern physics is not simple nothingness. Quantum fields possess vacuum states, and the properties of those states influence what particles can exist and how forces behave. If the present vacuum is absolutely stable, then there may be no lower state into which it can decay. If it is metastable, a transition could eventually alter the physical conditions within an expanding region. But even this does not automatically provide a meaningful successor to heat death. A vacuum transition could occur earlier, later, or perhaps never within any physically relevant region, depending on properties that remain unknown. It could destroy familiar structures rather than create a new cosmos resembling the current one. The deepest problem is that no confirmed theory identifies the present quantum vacuum as merely one temporary stage in a guaranteed sequence. The possibility remains open, but the final state of the vacuum is not known. That uncertainty leaves two very different kinds of cosmic future side by side. One is conservative and almost empty of novelty. The universe expands toward heat death and continues in that condition without a dramatic sequel. The other includes transitions beyond established physics contraction, bouncing, vacuum change, or the formation of new regions with their own histories. The first follows from extending the simplest current model. The second reminds cosmology that the simplest model may not remain fundamental across unlimited time. Neither position allows the title question to receive a clean answer. If heat death is truly the long-term destination, asking what happens next may be like asking what comes after an asymptote that is never crossed. There is always a later time, but no new era begins. If instead some deeper physical transition eventually occurs, then the word end may have been premature. What appeared to be an ending would become an interval between cosmic states. This distinction reaches beyond terminology because it changes what the history of the universe actually is. In one picture, cosmic history has a direction that gradually loses all structure and never recovers it. In another, the observable universe belongs to a larger sequence in which beginnings and endings are local transitions rather than absolute boundaries. Present evidence does not choose decisively between every version of those ideas because the relevant physics lies too far beyond direct observation. What can be said more securely is that the universe has already revealed how misleading simple words can become at cosmic scale. Beginning may not mean emergence from literal nothing. Empty space is not physically empty in the classical sense. Darkness does not mean absence of radiation. Death does not require disappearance, and an ending does not necessarily imply that something follows. The heat-death scenario sharpens that final point more than any dramatic catastrophe could. If the cosmos simply becomes colder, more dilute, and less capable of organized change forever, then there is no final spectacle to separate the universe that existed from a state in which it no longer does. Existence persists while history fades. The great structures disappear, but space-time does not have to. Energy remains, but useful differences vanish. Time can continue, but fewer events give that continuation content. The universe survives its own ending by becoming a place where ending and continuation are almost the same condition. Against that possibility, speculative models keep another door open. Perhaps the vacuum is not final. Perhaps expansion is not eternal. Perhaps the geometry of space-time permits cycles or transitions that current observations cannot reveal. Those ideas matter because they show that cosmology has not reached the conceptual boundary of what a universe can do. Yet they remain possibilities rather than promises. The most scientifically grounded answer is therefore also the quietest. After the universe ends, there may be no after in the familiar sense. There may only be a later and later cosmos, increasingly empty of structure, increasingly poor in usable energy, and increasingly difficult to divide into meaningful chapters. Or there may be physics beyond the present model that changes the conclusion entirely. The final mystery is not simply what follows the end. It is whether the universe possesses a true ending at all, or whether it only approaches a future in which almost nothing remains capable of happening. The universe may never reach a final instant that separates existence from nothingness. Its future may instead become quieter by degrees, with each great source of change disappearing into a longer silence. Galaxies slip beyond one another's horizons. Stars use the last of their fuel. Cold remnants endure where sunlight once existed. Matter may persist or slowly decay. Black holes remain through spans that almost erase the meaning of ordinary duration, and then even they return their mass to a universe already too empty to gather it again. What remains is not a void in the strict sense. Fields, particles, radiation, and space-time may continue. but the differences that once allowed the cosmos to build structure have nearly vanished. Heat no longer flows through great gradients. Gravity has little material left to assemble. The bright sequence from gas to stars, from stars to elements, and from elements to worlds has become part of a past with no obvious successor. There may still be later moments, perhaps without limit, but fewer events remain to distinguish one from another. And beyond that quiet future, science reaches a boundary of its own, a changing vacuum, a cosmic bounce, a renewed phase of expansion, or some structure not yet contained in present theory may still be possible, but none can yet be claimed as the next chapter. The most careful picture is simpler. The universe may continue without renewing itself, carrying the faint remains of its history into an increasingly dilute future. If so, the end is not a place where everything disappears. It is the point at which almost everything that once made cosmic history eventful has already happened, while the universe itself remains open, cold, patient, and still.